So we left off yesterday, we're doing operations with those degrees, minutes, and seconds. And we hinted at this structure called the unit circle. In order to work with that circle, I want to talk about some parts of a circle, just to review here. Oh, that's okay. Your circles don't have to be perfect. Remember, our circles, we have this part of a circle, which is called what? A radius. This part of a circle is called a diameter. In fact, that horizontal diameter like that is often referred to as a reference diameter. A part of a circle that went like this, connecting two spots, is called a chord. If we have a line that touches the circle but does not go into the circle, it's called tangent. And if we have a line that cuts through the circle, now the technical definition is it contains points both inside and outside the circle, it's called a secant. Those are all terms that we actually discussed last semester. One that we did not discuss involves this reference diameter. If I pick any point on the circle, that point has a value which is called its sign. The sign of a point is the distance from that point to that reference diameter. And remember, distance is always measured at a perpendicular or at a right angle. So that point has that sign, but every point has its own sign. This point would have a different sign. That would be the sign of that point. And this point has a different sign. So the distance from that point to the reference diameter is the sign. Well, back to our special circle that we're going to discuss here. This one is called the unit circle. And it's called the unit circle because the radius, I want to avoid writing there, radius is equal to 1 unit. We're going to place our circle on a coordinate grid. And we're going to have the positive x direction, this direction right here, is going to be our 0 degree direction. That radius that I just traced there in blue is what's called the initial side. Initial side because remember, angles are a rotation from one location to another. Well, the one side, the first side of the angle will always be located there at that radius. What's the length of that blue line I just drew in there, by the way? 1. Unit circle. Radius equals 1. So now I construct an angle by rotating a certain distance. That's my angle. I'm going to call it theta. Theta looks like that. That's just a Greek letter. Often when we're looking at angles, we use Greek letters for variables rather than our English letters. Notice that terminal side, we call it, that's at the end of the angle after the rotation, marks out a point on that circle right there. Well, that point has a sign. In other words, a distance from that point to that reference diameter. That is the sign of that angle. I'm sure many of you recognize that word sign as one of our trig functions. That's where the sign comes from, is from this unit circle. Well, one of the other terms we have that you probably recognize as a trig function is tangent. A tangent, the tangent is going to be tangent to the circle at the reference diameter. So this point right here is the reference diameter, the tangent is tangent to the circle at that point. Goes up like that. Where does the tangent stop? Well, if I traced out my terminal side through the circle to outside the circle, it's going to intersect the tangent and cut it off. So the length from that reference diameter up to where it intersects that terminal side, that is the tangent of that angle. The distance from the center out to where that terminal side, if I extended it, hits the tangent. Well, that contains points both inside the circle and outside the circle. It is a secant. That length is the secant of that angle. Those three, sine, tangent, and secant, are our three main trig functions. Now you might be looking at those thinking, well, but I've always had sine, tangent, and cosine. Where'd the secant come from? Well, there's another set of functions called the cofunctions. The cofunctions are the sine, tangent, and secant with the prefix co in front of them. Co, the prefix co, means of the complement. So cosine means sine of the complement. What does complement mean? I was waiting for that. Complement mathematically means that two angles add up to 90 degrees, or right angles. If I look at my picture here of the unit circle, the complement of theta would be right here. That has to be a 90-degree angle, doesn't it? Theta with a little bar over the top of it is the complement of theta. So now if I'm using that angle, my reference diameter becomes this diameter here, doesn't it? The vertical one. So what would be the sine of that point on that vertical reference diameter? Well, the sine would be right here, wouldn't it? That length, which is the same as this length right here, is the cosine of theta. It's the sine of the complement, the complementary angle of theta. The cotangent has to be tangent at that reference diameter, which is going to be up here. So that's going to go out like this until it intersects here. That is the cotangent of theta. It is the tangent of the complement of theta. And our distance, I don't know how to draw this in, I'm getting kind of cluttered, but from the center out to here, that length is the cosecant of theta. It's the secant of the complementary angle to theta. Well, what do all those things mean? Well, we're going to take a look at those values, and then we're going to take a look at how they relate to right triangles over the next 40 minutes or so. First of all, looking at that unit circle. I'm going to redraw it a little less crowded, hopefully. So here's our terminal side, here's our angle. This is the sine. This is the tangent. This is the secant. As our angle gets larger from 0 degrees to 90 degrees, what happens to the sine? Well, let's take a look at it. Let's go from where we're at here to here. What would happen to the sine? Goes from here to here. Does that get larger or smaller? It gets larger. So as we're going from 0 degrees to 90 degrees, as the angle gets bigger, as theta gets bigger, the sine of that angle gets larger. What happens to the tangent? Yeah, I extend this out here. The tangent has to get a lot larger too, doesn't it? How about the secant? Well, we just saw here it just sticks out a little ways. Here it has to go out a long ways to get to the tangent, doesn't it? The secant also gets larger. Yes, the secant is from the center all the way out. It's the whole piece. Now, this is going to tell us a couple other things about these values too. The sine, by the way, what is the largest the sine can be? At 90 degrees, it's going to be right there, right? What's that length? That's the radius of the circle, which is 1. So the sine of theta has a largest value of 1. At 90 degrees, what's the sine? Or sorry, at 0 degrees, what's the sine? This is 0 degrees here. What's the distance from here to my reference axis? 0, right? So sine of 0 degrees is 0. Sine of 90 degrees, we said, was 1. It can never go larger than 1. Can it go smaller than 0? Yeah. Here, if this were our angle all the way around like that, this is a negative sine, isn't it? It can go down as far as at 270 degrees. This would be the sine right here. That would be a negative 1. So the sine is always between 1, or negative 1 and 1. Sine can never go outside of that range. Secant. Actually, I'm just going to abbreviate it, SEC of an angle. What do we know about the size of the secant? Could I have a secant of 0.75? The secant starts here and it goes to the edge of the circle and it has to continue outside of the circle. What's the distance from here to here? 1. So the secant always has to be greater than 1 or less than negative 1. In other words, the secant cannot be between negative 1 and positive 1. Tangent, however, can have any value. Literally any value. So here's our angle here again. Only this time I'm looking at the cosine and the cotangent and the cosecant. As theta gets larger, from 0 degrees to 90 degrees, it's not sine, but cosine. The cosine of theta, now you think about it, the angle goes from here to here. What happens to that cosine? It got smaller. What happens to the cotangent of theta? Well, it goes from here to here. That cotangent gets smaller. What happens to the cosecant of theta? It also gets smaller. It doesn't have to reach near as far out to hit that tangent. There should be a pattern developing here, by the way. As we go from 0 to 90, all of our regular functions get larger. All of our cofunctions get smaller. Because the angle is getting bigger, the complement of the angle is getting smaller. Cosine. Well, since the cosine is basically the sine of the complement, we can probably come up that cosine has to be what? Just like the sine is always between -1 and +1. It has to stay within that unit circle, and the radius is 1. So it can never be larger than 1. Cosecant, in fact, I'm going to abbreviate, cosecant is abbreviated CSC of theta, either is bigger than 1 or less than -1, just like our secant is. Cotangent of theta, of course, can be any value, just like our tangent can be. At 0 degrees, what's the cosine? Well, at 0 degrees, cosine is this distance, right? That distance is just the radius of the circle, which is 1. At 90 degrees, what's the cosine? 90 degrees would be up here. Cosine is this horizontal displacement, which is going to be how much? 0. And that makes sense, right? As we go from 0 degrees to 90 degrees, cosine gets smaller. It's at its largest value at 0 degrees, which is 1, gets to its smallest absolute value of 0 at 90 degrees. As we go past 90 degrees, of course, the cosine starts to approach -1. Right? We'll look at those values as we go past 90 degrees in a little bit if we get time. But what I want to do now is I want to look at how did trigonometry go from being parts of a circle to being used on right triangles. Well, there are 4 triangles formed here when I put a specific angle on here. So let's put this angle on there. I have this triangle here where this is the sine of theta. Of course, this is theta. The length here is 1. That's just the radius. And then we're going to use this as the cosine. But I also have a bigger triangle that's formed here to here, where this length is the tangent of theta, This length is the secant of theta. And of course, down here, this length is 1, right? So I'm going to draw those triangles out over here. My first triangle, this is theta. This is the sine of theta. This is that hypotenuse, which is 1, which is just the radius of the circle. This is the cosine of theta. Then I have that larger triangle. This is still theta. This is still a right angle. This distance is 1. That's the radius across here. This is the secant of theta, and this is the tangent of theta. What can I say about those two triangles? Exactly, they're similar. They both have the right angle, and they both have theta in common. If 2 of the 3 angles are the same, the third angle here has to be the same. So they're similar triangles. In fact, any right triangle that has an angle of theta is going to be similar to both of those triangles, because all 3 angles will be the same. Now, a right triangle any triangle has 3 sides, but a right triangle has special names for them. This side up here is called what? Hypotenuse. The other 2 sides are called legs. And we're going to identify those legs according to the angle as either adjacent to the angle or opposite the angle. Now in this triangle, we are looking at this angle here, theta. Opposite means across from. Which side, the horizontal leg or the vertical leg, is opposite of theta? The vertical. So yes, this is the opposite leg. Adjacent means next to or touching. Obviously, all we have left is the horizontal leg, and that is adjacent. That is touching or next to the angle that we're looking at. Remember, those positions of the adjacent and opposite depend on the angle that we're looking at. We'll look at that in a little bit. But since theta is in that location on these 2 triangles, we have to use theta in that location here. If I want to define the sine, let's look at the sine here. So here's sine. And what I'm going to do is I'm going to do this. I'm going to relate it to the side of its own triangle that's equal to 1. Well, over to this triangle here, the brown one, which side of that triangle relates to the sine from this triangle? The opposite side. Which side relates to the 1? Hypotenuse. Sine over 1, which is just sine, is equal to hypotenuse, the opposite side over the hypotenuse. Length of the opposite side over length of the hypotenuse. Let's look at the cosine of the angle over 1. Well, the cosine, the side on this triangle that's the cosine, relates to what side of the other triangle? The adjacent. And the 1, of course, still relates to the hypotenuse. Cosine of an angle is equal to the length of the adjacent side divided by the length of the hypotenuse. Tangent. Let's look at tangent here. And we're going to relate it to the side that's 1 down here. So tangent, this side here relates to what side of my brown triangle? The opposite side. The 1 right here relates to what side of the brown triangle? No, careful. The 1 is this one now, so it'd be the adjacent side. So the tangent is opposite over adjacent. If I look at my secant up here, the secant of an angle, and I'm going to relate it to that 1. The secant on this triangle relates to what side of my brown triangle? Secant is the hypotenuse. That relates to the hypotenuse, right? And the 1 still relates to the adjacent side. So the secant of an angle is equal to the length of the hypotenuse divided by the length of the adjacent side. Now there's another triangle I can get out of this. That's the triangle up here that has the cotangent and the cosecant in it. What do I know about this angle here? Right there. Yeah, that's theta. Because this is horizontal and this is horizontal. Horizontal lines are by definition parallel to each other, which means this angle and this angle have to be the same. So that triangle is also similar to our brown triangle. I would relate the cotangent to 1 Well, the cotangent is the horizontal side, that's the adjacent. The 1 is the vertical side, that's the opposite. Cotangent is the length of the adjacent side divided by the length of the opposite side. And the cosecant related to 1. Well, cosecant here again is the hypotenuse, and the 1 is still the vertical side or the opposite side. So that's hypotenuse over opposite. So you can see all of our trig functions that you guys have memorized for right triangles, all they are is just relationships between similar triangles. Now, there are other relationships between them that you should note. You should note sine and cosecant. What's the relationship there? Yeah, they use the same sides, they're just reciprocal. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. Another relationship between cosine and secant, which is same type of thing, right? Cosine's adjacent over hypotenuse. Secant is hypotenuse over adjacent. They're reciprocals. And finally, tangent and cotangent. Tangent is opposite over adjacent. Cotangent's adjacent over opposite. We have a lot more to discuss with those, but we're going to deal with that more later. We did a little foreshadowing right before we left yesterday, using our unit circle. We can redefine angles. Angle theta here in degrees, let's say that that is 40 degrees. We said there's another way of defining angles rather than being a rotation, which is what degrees are. Degrees are rotations. We can define it in terms of the length of the arc it cuts on the unit circle. We said the circumference of this circle is equal to 2 times pi. Because it has a radius of 1, so it has a diameter of 2. So the circumference is diameter times pi, or 2 times pi. So the full circle would be 2 pi radians. In degrees, of course, a full circle would be 360 degrees. So we have that equivalency, just like we did in our linear measurements. Remember when we talked about converting like 8 rods into feet? We put 8 rods over 1, and we use that equivalency. One rod is 16.5 or 16 and a half feet. The rods canceled out. 8 times 16 and a half is 132 feet. We can do the same thing here. We have 40 degrees. We want to know what that is in terms of radians. We do 40 degrees over 1. We're going to convert. 360 degrees go on bottom. Radians go on top. The degrees cancel out. 40 times 2 pi is 80 pi radians over 1 times 360 is 360. And then I can reduce this. Now to reduce it, I'm going to ignore the pi, and I'm just going to look at the 80 and 360. What can both 80 and 360 be divided by? 10 will work. That gives me 8 pi on top and 36 on bottom. Then I can divide by 4. 8 pi divided by 4 is 2 pi. 36 divided by 4 is 9 radians. So that is 2 pi over 9 radians, or 2/9 pi radians. Make sense? Let's say I have 2 pi over 3 radians. I want to know what that's going to be in degrees. Well, that's already a fraction, 2 pi over 3. I'm just going to put the radians on top. My conversion factor, put radians on bottom and degrees on top. 360 degrees equals 2 pi radians. The pi's cancel out. I've got 2 times 360 is 720 degrees. The radians cancel out as well, by the way. 3 times 2 is 6. 720 over 6 is 120 degrees. Now, we could use a lot of textbooks use instead of 360 degrees over 2 pi radians. They divide out the two. They use 180 degrees and pi radians. It's a little bit simpler, but I always remember it that way because both of them are a full circle, so I know they're equivalent. What is the advantage to using radians? Why do we care? Why don't we just use degrees? Well, radians are actually a lot simple in a lot of engineering applications. You start talking about radial motion. Radial motion is things that spin. If this is my pivot here, I might have this spinning around. Well, I can describe that rotation in terms of radians per minute, or radians per second, or radians per hour, which tells me how that fast that's rotating. The nice thing about that radians per minute or whatever is I can convert that into a linear speed very quickly. Because remember, radians are arc length with a radius of 1. If the radius is not 1, the arc length is simply the radius times the angle in radians. So let's say my angle, theta, is pi over 4 radians. If the radius of my circle equals 4 inches, the arc length is simply going to be the radius, 4 inches, times the angle in radians of pi over 4. 4 times pi divided by 4 is just 3.14 inches. So that would be the length of that arc. Let's confirm that for you. This is my circle. Pi over 4 is actually 45 degrees. If this radius is 4 inches, find this arc length. Well, that arc length is found by taking the circumference, which is diameter times pi, so 8 times pi, right? Which is 25.12. And then we would take the arc length, that 25.12 inches, times our angle of 45 over 360, which is 3.14 inches. Where did the 45 degrees come from? That is the equivalent of pi over 4 radians. Pi radians over 4. If I did my conversion. 2 pi radians on bottom, 360 degrees on top. Radians cancel, pi cancels. 360 degrees over 8 is 45 degrees. What do you think? That was a lot of information in 45 minutes. What's that? Sure. I'll repeat it on YouTube later tonight. Page 537 to 538. Exercise 25-4. 1 through 15, the odds.